Shooters, reloaders, and conversationalists, welcome to PounderLabs. Today we're going to look at barrel tuning for rimfire rifles. Here's an overview of our presentation. We're going to focus on the Harel precision type tuners. We're not covering tuners with bloop tubes. Our focus is precision and long range type competition versus prone and international shooting. We're looking for performance gains in the 50 to 250 yard range. This started as a customer coming to us and asking about this, and then it fueled our own curiosity. We're looking at both the engineering component of this, vibration dynamics, and then there's also a statistical component looking at velocity data and hit on target dispersion. So some questions we'd like to look at: is there a structured way to approach this problem? Can measurable improvements be made? Are results reproducible? And can we improve the dispersion of low-cost ammunition? Before we begin, bear with me. I'd like to give you a little information about systems we developed in the past dealing with data acquisition, time series analysis, and vibration. I'll explain why on our next slide. This is a pre-crack Sharpie test using the Dynatop Impact Tester. This is a shaped charge system that was analyzing vibration and what's basically like an RPG type of explosive head. Here's a analyzing system developed analyzing vibration of drill string, which can go down 15,000 feet. There's synthetic seismogram. We're modeling earth response from impact, dynamite explosions, and such. And then there's what's called a triaxial downhole formation testing, where we're listening for cracks in rocks acoustically and trying to predict where the formations are yielding for better oil production. The reason for going through a little background in the previous slide really isn't to toot my own horn, but to make a couple of points. Vibration is a large and important topic in industry. It's heavily studied with large engineering investments. So when we look at barrel tuning, really it's just not that difficult. It's just another vibration problem. But we've seen over the years many opinions, postings, and so forth. A lot of people don't really understand what's going on here and waste a lot of time and money and don't really have the background. So I want to make the point that this topic is pretty familiar to my training, and we hopefully can go through this presentation and provide a foundation that can help others. Let's take a look at the rimfire tuner landscape today. We can break this down into a couple of categories. The rimfire bench rest, prone and international type things. Tuners are universally used. They're almost all single distance, typically 50 yard, 50 meters. Very high-end purpose-built rifle used in rests. These are single shots. The very best ammo is used. And both accuracy and precision are very important, and there's extensive testing done. This is what we call a very strong baseline of performance history. What we're interested in is precision rimfires, like left class, long range. Well, here tuner use is kind of a mixed bag. We're dealing with multiple distances, different types of supports, bipods, and so forth. And then there's a lot of running around from stage to stage. There's a lot of different rifle builds. Some of these are swizzle 3-position and bench rest. Other ones are tactical systems with various barrel profiles. These are almost all magazine fed. There's a broad range of ammo used, and the quality of testing on the firearm and ammo is everywhere from pretty strong to pretty iffy. But we'll say that usually not a strong baseline of performance history. We can break down ballistics into specific zones or stages. First of all, internal. This is the firing of the round in the barrel, in the chamber. There's the transitional or intermediate, is when the projectile, the bullet leaves the bore. And then there's the external. We're very familiar with these principles here with ballistic solvers in free flight. And then the terminal ballistics is when it hits something. We're focused in on this transitional zone. This is the domain of muzzle crowns, tuners, brakes, and bloop tubes. So that is the direction we're going to take as we drill in more deeply. Barrel vibration is common in all scale of gun and firearms, air rifles, small arms, tank cannons, and so forth. It can be a complex movement, creating what we call a high degree of freedom model, and it's often hard to see and hard to measure. You can see from this vintage diagram here, just everything that's involved with once the bullet starts to leave the bore. So can we parse this problem down a little bit? As mentioned on the previous slide, we're going to focus on this transitional zone. We're going to measure what we can. We're going to make some simplifying assumptions and then hold some things constant. One of the most important simplifying assumptions is even though the bullet can fly all the way around here, gravity plays a very important role. So if we look actually down the bore, we see these force vectors on where the barrel can move, but you'll see these force vectors more predominant because of the effect of gravity. That's going to be something very important that comes into play a little later. Now the reason we're focusing on rimfire is unlike centerfire, where you can load ammo and do some tuning there, you really can't do that with rimfire. So you need to select and test, and if you're going to do anything, you need to tune the firearm. So it's a different problem, but a lot of the things we're going to discuss here are also applicable to centerfire. We need to take a closer look at these two important types of vibration. The first is harmonic motion. This is what you have when you strike a guitar string. It's what we call a steady state response. It's a continuous signal, and it's simple and not time dependent. Every time you strike the string, you're going to get exactly the same thing. This is a fairly simple degree of freedom model. Things like tuning forks, a weight on a spring, a swing. These are common examples of simple harmonic motion. The other one is called transient vibration. This is from an impact, or in our case, when the cartridge is fired. This is an impulse signal and is complex and time dependent. So in the case here, where something is struck, you'll see this kind of behavior before it goes down to steady state. This can create a high degree of freedom model. These things create different types of waves. The stationary wave, in the case of string guitars, doesn't travel, vibrates back and forth, and we describe these with nodes and antinodes. On the other hand, progressive waves do travel. We describe these with crests and troughs. Here's a case of a bullet moving through space, and you can see these waves created, definitely moving, and certainly things like dynamite and certain things like earthquakes create these kind of progressive waves. So it's important to understand the difference here. Our particular problem of barrel vibration is a combination of both of these. There's both a transient response and then a steady state response. Let's break this down further. Let's now consider the frequency response of vibration. We're going to make the simplifying assumption and model the barrel as a cantilever beam. There's a lot known about cantilevers. We see things in the time domain, where magnitude is a function of time, and we can convert this signal into the frequency domain. We could use a signal processing system called a spectrum analyzer to see what the spectrum looks like. But numerically, we can also use what's called the fast Fourier transform. And in the frequency domain, we're now looking at magnitude as a function of frequency. And we can convert back to the time domain using the inverse Fourier transform. So let's look at the motions, the modes of vibration we can see in our barrel. 1, 2, 3, 4, is how these modes are described. This is what the barrel looks like in the time domain, if you could see it. This is what it looks like in the frequency domain. So this is the lowest frequency, and you see the spike here, and you'll notice as the modes go higher, the frequency goes higher, and the signal gets smaller. Some of the things we do in the frequency domain are a lot simpler than doing them in the time domain. So here we just simply add up these frequency responses and we get the combined frequency response of the first 4 modes of barrel vibration. We can use the inverse Fourier transform to put that back into the time domain, and we see a funky waveform like this. So the higher order gives higher frequency. You can sum to get the complex frequency response, move it back in time to see the complex waveform. Well, what do we do about this? Once we understand the model, we've got 2 options. One, embrace the barrel movement, or eliminate it. Kolbe studies rimfire barrel vibration, does theoretical work up so he has some viable models. He built the following apparatus. This measures vertical displacement, very lightweight sensor, and this senses when the bullet travels out the barrel. Others researchers did this experiment. They attached a displacement sensor onto the end of a skinny 30-06 barrel and fired it. And here's what they recorded. Notice the vibration as we looked at, like we did in the previous slide. And look at the time scale though. This is 500 milliseconds. That's a half a second. If this bullet's traveling at 2,800 feet per second, while this barrel is vibrating, this bullet's already 500 yards downrange. Kolbe's experiment looks at this time scale. So we have 2 different bullet traces, difference in velocities, and you'll see these little red spikes. That's when the bullet transitions through that sensor. The way his equipment works is it's constantly gathering this deflection data. So once the signal has been triggered, he can slide this one back to align the spikes here where the bullet exits. Well, he's interested in this area right here. So you'll see on this bullet the exits when the barrel's pointing up, and on this one the barrel's pointing down. The Kolbe experiment demonstrates what's called the positive compensation model. Let's use these excellent diagrams from Varmint Al's site so we see how this works. If we bolt the barrel into a rigid vise and fire 2 different rounds, the lower velocity is going to follow this trajectory out to 50 yards. The higher velocity is going to go higher and will have a different impact point. Now let's say the barrel is free floating and we have the ability to time it. Well, if we get it on the uprise, we have the faster bullet going out first, following this blue trajectory. The lower one actually takes a higher trajectory, so the time of flight is a little different, but the impact point is now the same. Let's zoom in on this particular rising, falling part of the barrel vibration. Here in the blue area, if we're catching on the upswing and the faster bullet exits earlier than the slower bullet, we get this kind of behavior, which is good. But notice the other side, if we catch it on the downswing, we can see that it actually makes it much worse because the faster bullet exits earlier and gets there quicker than the lower speed bullet. So you'll notice the time scale here. We're down around a millisecond from the previous Kolbe experiment. His whole thing was about three or so milliseconds. This is like with a little more than 1 millisecond. So it's important to appreciate how fast this is going to happen. So positive compensation is going to be very range dependent, and you have to match carefully the rifle and the ammo lot. But where it can probably hurt us is recognizing what we're doing with precision rimfire, that we're going to be looking over multiple range differences. So we can't tune just the one point. We have to think about over a 200-yard plus range. The other model is called Muzzle Stop. This is championed by Bill Calfee and others. It's based on the idea of harmonic motion and rooted in what we call the bound model, like we have a vibrating string, and then this is extended to the cantilever. So let's take a look at how this harmonic vibration works. Let's just say this is the length of our barrel. If we looked at the fundamentals, you'll see this is a half wavelength, but this point here, the muzzle's not moving. So as we go to the second, third, fourth, and fifth harmonic, it doesn't matter which one you're dealing with, but the point is the barrel is stopped. It's not really stopped, that's just what it looks like. This is whether high or low velocity exits at this point, it would not be any different. Here's an article from '94 that's explaining the Calfee experiment. He observed the vibration of an aerial on his truck, and this is what he saw. You now can recognize that this vibration going on here is in between the fundamental and the second harmonic. So he's envisioning that this is how a barrel can vibrate, and you can see it's going up and down here. So the idea is to add weight, if you will, make this a virtual node to clamp out that vibration. So you put the weight here, it becomes more of a bound problem, and you can see that this right here is the second harmonic, but at the end of the barrel, it's not moving. It's a stable point at that node. Now, if you put even more weight on, you change. We've now gone into the third harmonic, but the point is the barrel's not moving. So let's take a look at what this means compared to the positive compensation model. So we have two schools of thought. What I call the Kolbe-Harold model, which is positive compensation. It embraces movement and catches the antinode. And there's a lot of finite analysis that's applied to this kind of movement in industry. So the strong points, we see this kind of motion in complex problems. We get a modal shift, it reduces the degree of freedom, we get our damping, but we think there's more study that's probably needed for a better understanding of this method. The Calfee muzzle stop models based on the idea of barrel harmonics, a lot of physical measurement, and now we're reducing or minimizing muzzle movement. Strong points, a lot of practical experience, heavily used by shooters. It's a simpler concept, and we're getting a damping. Oxum razors is an idea that says when you're comparing two things without complete information, it's a good idea to start with the simpler one. So for example, here in North America, if you hear hoof prints, you should think horses, not zebras. But you got to be careful because if you're in South Africa and hear hoofs, it very likely could be zebras. Now's a good time to pause and consider. If you're shooting without tuners and getting good, tight, round groups, you're fortunate and they have your ammo and rifle already giving optimum results. Stop. A tuner's probably not going to provide much value beyond that. But if that's not the case, consider looking at a tuner. By adding a tuner, it does the following. The additional mass reduces the amplitude of vibration, decreases the natural frequency by decreasing the lower mode frequencies more than the higher ones. We illustrated that on previous slides. And then we increase the barrel's vertical sag due to the extra weight. This would make the vertical plane the preferred plane of vibration. This goes all the way back to one of our earlier assumptions, and we told you how gravity plays into this. And then what we do is move mode 2 closer to the muzzle, thus making it a stopped model. If you've been hanging with me through this whole thing, I now have some good news. Regardless of which approach you favor, tuning is done the same way. There's a couple of options for barrel tuners. There's muzzle mount and mid barrel. Here's a mid barrel here. We're going to be focusing on the muzzle mount. It's just simply easier to illustrate our points. The tuner focus is with the CZ457 24-inch slender barrel using Harrell tuner brake shown here. Also, the CZ457 with a shorter, more stout barrel using the Harrell Rimfire tuners like shown here. Our approach experimentally is in controlled conditions. We're going to go to a indoor 100-yard range, get on heavy bench. We're going to lay out experimental design. We're going to get velocity data with the lab radar. We're going to use a weather meter for our environmentals to get speed of sound and air density. And for hits on target, we're going to look at groups at 50 and 100 yards, scan and measure these with the on-target software and do our statistical analysis. This will all be covered in the next video called Rimfire Tuning for the CZ457 in practice and example. So hopefully you'll join us for that. And now something for my terminally curious viewers. Paul Klipsch was a Renaissance man in the study of vibration. He's a legend in the audiophile community and inventor of the Klipschorn system, speaker system shown here, and the founder of the Klipsch Company. He studied vibration in many fields beyond audio, studied seismic and mechanical. For small arms damping, in 1939, he invented a device and received the patent for that in 1942. Here's a page from the patent application. Does this look familiar? Very much a type of device that we would recognize as a barrel tuner. And we can see that all the way back before the war, World War II, others have studied these problems, and it always benefits us to look what's been done before to see if we can improve things going into the future. This completes our presentation, and as you're thinking about subscribing, please look over these important notes and disclaimers. They're here for your protection and ours. Thanks for watching. Be safe. See you soon.